We already talked a lot about acoustics. It's normal, it's an acoustic seminar, of course, and a little bit less about thermal comfort. And in my presentation, I would like to assess the question: is it possible to combine acoustic and thermal comfort in tabs building? So for me, tabs building, it's the number three we already discussed there. And just to remind that thermal comfort in such kind of building depends on convective exchange with the ceiling, but also depends on a radiative exchange with the ceiling. The question is, what happens if we install horizontal acoustics panel, how this will modify the thermal exchange with the ceiling and how it will modify the thermal comfort. When Ecofon came 3 years ago to see me about this question, the first thing to do was to make a kind of literature review to know if there is already some work done on this question. So I've looked at this article, and we saw that there is many different articles with some case studies, some thermal models. Very interesting work, but nothing really clear, not a real clear answer. So the first thing done after this literature review was to try to summarize the results in one graph to have a kind of big picture. And we obtained this graph. So what are we looking here? Here, it's the tab's cooling power. In fact, it's here in percent. It's the ability of the tab ceiling to cool and to restore your thermal comfort in the room. And here it's the coverage ratio. If it's 0, it's a clear ceiling. And if it's 100, it's a totally covered ceiling. And here, all the different points are points took in literature paper, in scientific literature review. And what we can see is that we have a very broad number of points, but we have a kind of linear correlation. I insist here, it's a very large view with many different case studies, many different situations. It's a very big picture. It's just to have a kind of very general view. And we can estimate from this that covering 70% of the ceiling with horizontal panel will give you a reduction of around 30% of the cooling efficiency. Okay, this was interesting. It was a literature result. But the question was, okay, what can we say about thermal comfort? So in collaboration with Ecofon, we did different case studies. The first one, I'm sure that you've already heard about it. What's the WUPA case? It's WUPA, it's the name of a tower. It's in Lyon, in France. And in this tower, in 2 rooms, we install one nothing, and in the other some horizontal sound absorbers. And we observed that on average, with a 50% coverage, you increase your operative temperature, so the temperature that you really felt, not the air temperature, but the operative temperature, by 0.3 degrees. So it's a very small increase. It's not zero increase. And this was very interesting because it was our first measurement. I should say it was the first experiment for us also, so we made some mistake. We learned a lot. We had some interesting results, but we decided also to make a second case study in the Freiburg building T. It's in Germany. And in this building, we install more rooms with sound absorbers and more rooms without any sound absorbers, and we compare and we collaborate with the Fraunhofer Institute. And what we saw is that here there is no clear correlation between the ceiling coverage ratio and the time spent in the best comfort category as defined by thermal comfort standards. So why? In fact, there is an effect of the sound absorbers on thermal comfort, but this effect is masked by many other effects because it was a real building with a real occupant. For example, opening the window, increasing the cooling or the heating system, even if it was not necessary. So all this masks the real impact of sound absorbers on the thermal comfort. During the time of these 2 measurements campaigns, there was also some other article more focused on yep, yeah, sure. Uh, uh, yep, 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 yeah. But it was it's I would say it's the real situation. It's even if you ask to people to not open the windows, they will open just because they are too warm or too cold or whatever. Yeah, yeah, yeah. There was. Yeah. Yeah, exactly. It was one of the interesting thing that we saw. It was that here it's, I will say, the real life. It was not the measurement at lab scale where you can control everything, where you are in very clear condition. Uh, at the beginning, before the measurement, we think that maybe we will see a clear effect of the sound absorbers on the thermal comfort, but in real situation, we saw a lower effect than expected, and it was very interesting for us to measure this. So that's for the measurement and for the real situation. The problem is that at the same time, as we already discussed, sometimes we had some feedback from customers saying that okay, we don't really know how the sound absorbers will impact the thermal comfort in tabs project. It has been mentioned exactly. So because we are not sure, maybe we will be safe and limit the sailing coverage ratio. But we saw that in the measurement and in the experiment, the impact of sound absorbers exists, but is not so important. So what can we do? In this situation, we discussed with thermal consultant, and we saw that many thermal consultants use a software which is called Transistor. It's a software used to design the thermal behavior of building. It's a very ugly and old software, but it works. And the problem is that today this software, well used, is not able to correctly model the free-hanging sound absorbers. Why? In fact, for a lot of different technical reasons and assumptions made in the thermal model. So what we decided to try to provide a plugin, so a new piece of software for this Transistor software to help thermal consultant to use to model the sound absorbers in their project. Just the techie slide, because you know I'm the researcher guy, so I love a lot of equation. We made a complex model with different assumptions, but basically the idea behind is to say that we will consider the room, the wall temperature, the air temperature, and the sound absorbers in this room, and we will be able to play on the distance of the sound absorbers through the ceiling, and of course on the ceiling coverage ratio. This software may be used with Transys with some different files and plugins, but we can discuss this later. And the question was, okay, making a model, it's a good idea. Making a good model is better. So we tried to compare the outputs of our model to some measurement, and the first graph we saw, and so here I took the same graph, and here you have the point, the red dot, which are the results of the thermal modeling. It's good results. It's not so far from the main line. Just two remarks. The first one is that, as I said before, this graph is a very big and broad picture. So it's a very it's a view from very far. So okay, our model is able to represent the average behavior of the average impact on the behavior of sound absorbers on thermal in tabs buildings, but it has to be adapted to some situation. And second, this is based also on mainly on lab scale measurement, not only on a real situation. So we did some other validation in collaboration with Niels here, and we saw that we obtained very good agreement on the cooling power and also on the air and operative temperature. I will not detail this too much. We can discuss this just after. But the main thing is that our model, I think, is good to reproduce the impact of sound absorbers on thermal comfort in TAPS building on the average. Of course, we can improve. There is some room for improvement, but as a first step, it was good. And now, what we are doing, we are giving this plugin to real people, to real thermal consultant. So I'll call this the crash test because we worked on this and now we will see if it works for real. So of course, if you are interested to try it, I think it will be, of course, okay. And tomorrow, we would like to improve maybe this model and to try to work on other situations from this first step. So we already discussed about the baffle, the question, because in our model we are working only on horizontal sound absorbers, and also to work better with the impact of ventilation. What happens in the case of high ventilation and in other types of TAPS buildings. This is for the future. I think the models that we have already today may give us a good basis, but I think also that there is still a lot of work to make this. Thank you.